So let's see how we can solve this kind of equations. Suppose we have a standard form of ordinary differential equation like this. We call it explicit first-order differential equation set, where x is a vector, and f is also a vector, where x is called the state vector. And this one is also regarded as the state space form of a nonlinear system. So suppose there is such a system, how can we solve, how can we simulate the system? I will first give you some idea on how to solve this kind of problem numerically, but it is not quite necessary for the course because we can use Matlab commands to solve the problem directly. Suppose x is a scalar, and suppose we know x0. X0 is here. If we add x0 to this equation, and if we select x1, even t equals to 0, we have x0. What about if t equals to h, where h is very small? What is the number of xt?
How are you? Good, how are you? Good, good. So where are you going though?
Well, if h is very small, we can approximate the first order derivative of x. From left hand side we have x. T is h minus fx 0 divided by h equals to f 0 x0. And finally we should have h equals to f0 plus h f t. And this is an approximate way to find xh. And we have to use this way. We can find the xh approximate solution of xh here. And then from this point, we can also use the similar method to find another solution. And we can use this method to find all the solutions. So this is this is just a sketch showing the numerical method solutions to the problem. If you are not quite familiar with this kind of solutions, just ignore them. These are the mathematical details. And apart from this simple method, this method is called Euler's algorithm. Apart from this simple method, we can also have other kind of more complicated methods, such as Runge-Kutta method, where we have to calculate 4 intermediate variables, k1 through k4, and then take the weighted sum and find the next point. So this is another method which is often used in numerical algebra courses, numerical analysis courses. Based on this method, I have written a Matlab function called RK4, which can be used directly to solve differential equations. And it is also noted through examples that actually if you try to solve differential equation, you will find that the Euler method or Runge-Kutta method may not be very accurate. So modern solutions to differential equations may use improved version of Runge-Kutta method, which is called Runge-Kutta-Feinberg method, which uses 6 KIs and uses the sum of weight to find the next point. So I'm not going to present in too much detail about the solution or about the numerical method. And what I need to stress here is we can use Matlab functions such as OD, O5 to solve the differential equation directly rather than going too much detail about mathematics. We can use this function to find the solution directly. And now let's first write out the standard form of differential equations. We have to use this standard form. Suppose the differential equation can be expressed by this form, and if we know x0, then we have to use the Matlab function to solve the problem. If a differential equation is not given in this form, we have to try to use other methods to convert it into this form. So this is the standard form we must use. So this is the first step. If you have a differential equation, you have to rewrite it in this standard form. This is the first step. And the second step is how to write a Matlab function to describe this kind of problem. And the third step is to solve the problem. I will demonstrate this one through an example later on. And the fourth step is use a plot to visualize the result. And finally, the most important one is how to validate or verify the result. So these are the procedures we must follow to solve a differential equation. Now let's consider an example first. So it is already listed here. I've just added this slide.